How do you do, ladies and gentlemen, and boys and girls and teachers? I'm Julius Sumner Miller, and physics is my business. And our special business today is more on sound waves and more deliberately on these two matters, frequency and pitch. When we speak of a sound, we ascribe to it a certain pitch, A, B, C, D, E, G. A, for example. If I strike A, let me do that. Here I have a bar, which I'm going to strike. That bar has a certain mechanical motion so fast, we call it the frequency. It gives rise acoustically in my ear to my brain a property called the pitch. For example, I struck a bar which vibrates 440 vibrations per second, and we call that A. We call that A. If I struck a tuning fork, let me find one here. I will strike a tuning fork, quite like so. That is vibrating 256 vibrations per second, and we call that middle C. So, the mechanical behavior of a vibrating system, we call its frequency, and what emerges acoustically, we call the pitch. Let me illustrate. Here is a metal, and by the way, it needs to be remembered, and very clearly, that in order to have a sound, we must have a vibrating system. And for sound energy to be propagated, there must be a medium for it. Because remember, sound waves are compressional waves, and there has to be something to compress. So here is a piece of steel plate. I'm going to flex it. Listen. It has a certain frequency. It's giving rise to certain pressure pulses that advance upon the microphone and upon my ear. I spoke of pressure pulses. I want you all to try this adventure. It is quite remarkable. Hold your arm in this matter and do some talking firmly on the arm. I say that I feel the changes in pressure on my arm, which emerge from the pressure pulses coming out here, a result of the behavior of my lungs, and the voice that I have is governed by the frequency of my vocal cords, how my mouth is shaped, the position of my lips, where my tongue is, and whether I have teeth or not. A very important thing. Here is another sheet of stuff, a bigger sheet, bigger, more inertia, likely to have a lower pitch. Yes, it does. And here is a bigger sheet of the steel, the like of which I had in the first place. Bigger, more inertia, lower pitch. Lower pitch. Let me speak more of that frequency and pitch business. Here I have some metal discs, which are notched. This one, I hope you see, has 4 notches. That one, 8 notches. That one, 16 notches. And this one, 32 notches. Now, if I put this shaft in a rotating motor and spun it, and held a card or a flexible piece of steel against this one, I would get for each revolution 4 pulses to the ear. This one would give me 8 pulses, this 16 and this 32. Hence, although they have the same angular velocity, they have different frequencies of pulses reaching my ear and therefore different pitches. Let me show you that here. I have a disc with some holes in it. And I call your attention very especially to the following. The outermost row of holes has the mostest holes. The inner, the next inner, less holes, less holes, less holes still. All these 4 rows have their holes symmetrically separated. The innermost row of holes has its holes unsymmetric. So, if you give me your attention, I am going to try to show you the difference between music and noise. Now, I'm going to have some difficulty with that because for some, boogie-woogie is music, but for some of us, it is not music. Watch me. I'm going to rotate this at a certain speed and drive a stream of air through successive rows of holes. Watch this now. Watch this. Watch. Now I'm going to go faster. Now I'm going to go faster still on the outermost row of holes. Watch it. So you see, the higher the frequency, the higher the pitch. Now all of these emitted pressure pulses were pleasant sort of to the ear. We call that music. Not only that, but the frequencies can be written in a simple mathematical way. Now I'm going to proceed from the outermost to the very innermost, and there the lack of symmetry will tell us something about the difference between sound, music and noise. Now watch it. Watch now. Watch. I don't think we could classify that innermost one as music. More on vibration frequency. Notice a meter stick. A meter stick, I fix it to the table so, with such a length hanging over. Very high frequency, very high pitch. Lower pitch, lower pitch, lower pitch, lower pitch still. So I have tried to connect for you pitch and frequency. Consider this, which Galileo observed. Here is a silver coin, a $50. It is milled on the edge. I hope you know why it is milled on the edge. I'm going to run my thumbnail over it, doing exactly what Galileo did in the 16th century. Listen. Now I'm going to take a silver dollar, and I think we'll have a different pitch. Why? The milling is at a different rate, and the inertia of this is of a different sort. Listen. Let me take a quarter, a dime. Remember, something is vibrating. Or just tearing a piece of cloth. Here is a piece of cloth. Listen. Vibrating system. Here is something else that I'm going to tear. Different pitch. Or consider a board which I rasp with a large file. Listen. Certain pitch. Finer file. Higher pitch. Very clearly that. Very clearly. Or take a deck of cards. Listen. Listen. Or a larger deck. Larger inertia, more mass, lower pitch. Now, more of the same. You remember the flexible steel plate, the flexible brass plate. Larger. Now, question. Here is a plate. Listen carefully. Listen. 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 I hear nothing. Somebody says, it ain't vibrating, Professor. Oh, it is vibrating, but at such a very low frequency that it is below the audibility of the human ear, which leads me to remark that the human ear range goes from about 16 vibrations per second to about 16,000. Some say 20 to 20,000. Now, the vibration frequency of this lead plate was so very low. Now, consider, again, the tuning fork business. Did I not say that if I strike a fork, it has a certain frequency, therefore it emits a certain pitch? Later in this series, I will show you a wonderful thing. Here is that bar that I have already struck and made sing. And you'll notice that bar is fixed here and fixed there. These are positions of rest in the bar, and they are called nodes. And the bar is really doing something like that, which I will show you in another lesson. Now, how about a tuning fork? Well, a tuning fork is a bar. There is the bar, and the tuning fork was bent up so that these two nodes are very close together, and a handle was put on. And thus is the mechanism of a vibrating bar. More on the same, but of a different complexion. An enchanting little business that is essentially a toy, but which can be made to emit music. Here is a prismatic rod, rectangular rod, which is notched. And you see that if I run this the stick across the notches, it goes into that hole and up, into that hole and up. Here is a little propeller on the end. Watch the behavior of the propeller. The propeller has a frequency governed by the frequency of the notches on the stick. Mark you too, this rotated this way when I stroked it here. Now watch it. Aha, aha. And in another lesson, I will talk about compounded harmonic motions which give rise to some beautiful things. So let us sum it up. Let us sum it up. The mechanical behavior is the frequency. That which emerges acoustically is the pitch. Good question. An orchestra tunes up. The maestro comes in and starts, but before he starts, I ask, by what instrument does the orchestra tune itself? Everybody thinks it is the piano, but that is not right. Now, why is that not right? Because the piano has metal strings, and metal strings change in length, and therefore in tension, and therefore in frequency, and therefore in pitch. So there is one musical instrument by which the orchestra tunes. I leave you now with this question. The auditorium gets hot, the musicians get hot, the instruments get hot, and the instruments get out of tune. Question, what happens to the wind instruments, and what happens to the stringed instruments? And we shall see this on another program, because all that emerges from vibrating bodies is sound of some sort, and some wonderful to hear. And I shall be with you another day.